It's my great pleasure to present Dr. Masahiro Tanaka, who is coming to visit us today from Microsoft Research and the DeepSpeed team. He has over 10 years of research experience in large-scale distributed processing and is a principal researcher on the DeepSpeed at Microsoft. He has contributed to large-scale deep learning training with over 2,000 GPUs, including the Phi-3 model, and developed innovations such as DeepSpeed Ulysses for long sequence training and DeepSpeed FastGen for fast and efficient inference. Has received numerous awards, including the first place in the PyTorch annual hackathon and first prize at the Advanced Technology Award and the Docomo Mobile Science Award. So,
thank you for the kind introduction. I'm Masahiro, nice to meet you. I'm from the DeepSpeed team at Microsoft. It's a great pleasure to give a talk here. Thank you for joining. Today, I will talk about scaling deep learning with DeepSpeed, challenges, solutions, and practical lessons. That's what I do today. But first, as everyone knows, the scales of deep learning models have rapidly been growing. So yeah, as I said, I remember BERT very well. It was released in 2018. The model had 340 million parameters, and it doesn't sound super large today, but it was actually large when it was released. I remember that we were struggling so much to fit the model into GPUs. Each GPU has only 16 gigabytes. And then we are trying to pre-train the model for Japanese language because I was working for National Research Institute in Japan. So within only 2 years, GPT-3 was released. The model has 175 billion parameters, which is actually more than 5 times larger than BERT. This is crazy. But even after that, the model scales continue to grow. And then now some of the recent models are said to have more than 1 trillion parameters also. But on the other hand, GPUs are also kind of progress, but the memory size and the clocks of GPU have been growing almost double in 2 years. The progress is also impressive, but if you consider the growth in model scales, I would say this is pretty limited. Also, in terms of the training cost, also the size of the training data has been growing. For the recent models like Phi-3 or Llama-3, at least you need to use a few trillion tokens. For very latest models like Llama-3, it's even more. But as the training cost is proportional both the model size and the data size, it's very, very challenging to kind of train these kind of models recently. So the DeepSpeed was originally proposed to address these kind of scalability and efficiency issues. According to the official definition, provided you can find it on our website, DeepSpeed is a deep learning optimization library that makes distributed training easy, efficient, and effective. So today I want to talk about some DeepSpeed features and kind of the next steps in this field. So in terms of efficiency, it is proven to show high performance from a single GPU to more than 10,000 GPUs. Also, DeepSpeed is very easy to use. You can run it out of the box with minimum effort. The last point I mentioned here is democratization. Sometimes people say it's almost impossible to run the latest model because it requires a lot of computational resources. But DeepSpeed offers you to access the model with limited computational resources. How much is a contribution to the ecosystem in this field? So we have so many tools in this field. The DeepSpeed has been used to train many foundation models, like starting from Turing NLG, GPT-NeoX, or Blue, or Phi-3 Arctic, or something like that. It is also integrated with many other frameworks like Transformers, Accelerate, or Lightning, and even for a complicated training pipeline like OpenRLHF, they use DeepSpeed to scale up the training. One unique feature of DeepSpeed is it actually supports various platforms and various accelerators, not limited to CUDA. It also supports Intel XPU and Huawei and few more accelerators. Actually, recently I heard that AMD people are really enthusiastic to invest in us just to extend the support for their platform. And lastly, superiorly DeepSpeed is mainly used on the public cloud or the on-premise clusters. Actually, we recently released even Windows version. If you have a Windows laptop, you may be able to use it. Actually, I haven't tried it. So some people said, yeah, it worked. Sometimes they have the issue. Anyway, although probably this is not a major usage, we are trying to extend this. So also I want to say that we are very popular in this field. DeepSpeed has more than 35,000 stars on the GitHub. This is actually 10th in the ranking out of 8.1 thousand repositories of Microsoft. And it is also downloaded more than 30 million times. If you look at the numbers of transformers and PyTorch, number of stars of them, they have 135,000 and 83,000 respectively. Yes, we are smaller than that, but still considering the user base, because our target is for distributed learning or efficient training or something like that. So if you think about our user base is limited, I would say the number is pretty good. So it suddenly rose. So that was when we released a DeepSpeed chat. This is a framework to train RLHF pipeline. So as we have so many different issues in training and inference, so DeepSpeed also has many features to address them. The most popular one is Zero. Now, so many other frameworks also support the same idea. But anyway, so we have more features like 3D parallelism to train a super large scale model, or DeepSpeed MOE, or yeah, efficient training for MOE model using expert parallelism, or many more. Today, I want to talk about a few important features of DeepSpeed. And also some features which are especially important in the recent trend, like MOE or long sequence, or I don't know, something like that. Okay, first, let me talk about. Wait, sure.
For users, for normal users, like for example, if I were to use DeepSpeed, do I treat it like a wrapper, similar to something like PyTorch Lightning or
yeah, it's something like that. Just you can pass your own model into DeepSpeed initializer, and then that will return the kind of wrapped model. And then you can access most of the DeepSpeed features, especially for important features like Zero. But if you do something very complicated, like if you want to combine different parallels like Zero and the pipeline parallels and tensor parallels, probably you need more. But we also have the code base to this kind of complicated training. In that case, what many users do is, yeah, depending on your task, we have the examples, then so they can reuse it. Thank you for the question. Then, so first, let me begin with Zero. So as I already mentioned, the model scale is a big challenge, especially when you scale up the model, the memory is an issue. Zero is a technique to mitigate that memory requirement. But before I explain how Zero works, let me revisit the breakdown of the memory usage in training. So although many people are actively looking for new methods in training, but the mixed precision is still one of the most common way. Mixed precision, if you have your model has n parameters, in that case, you use a lower precision format for parameters. Then if that means FP16 or BF16, that will be 2 M bytes. Then the same goes for gradients, that will be 2 bytes as well. But for optimizer states, usually you use FP32. That will be actually 16 bytes because in mixed precision, you need copies of parameters and gradients in FP32. Also, the variance and momentum for Adam must be in FP32. In total, yeah, if you have 1B model, 1B parameter model, that will be 20 gigabytes. And this is pretty big. The old model is only 1B, but still you need 20. Also, in addition to that, you need good batch and activations. If you are not using activation checkpointing, activations, the memory for activations will be also significant. So, but the zero is designed to mitigate this memory requirement. The basic idea is zero partitions the data for that. I mean, data parameters where it's optimized as the 3 different types of data. So with traditional data progression, you replicate all these data on all data parallel processes. As this figure shows on all GPUs, they have the same data. But zero actually, and then so partitions the data. But to balance memory saving and communication overhead, we have 3 different modes, which we call deep speed 0, stage 1, 2, and 3. So stage 1, just partition optimizer states. But this works very well, as we already saw. The major memory usage is by optimizer states because it's especially in mixed precision, because it's in FP32. But if you have sufficient number of data processes, so you can drastically save the memory. Also, the stage 1 doesn't increase the communication overhead a lot. This is also good. So actually, in terms of the communication volume, it doesn't change. But for the stage 2, you also partition gradients. And for stage 3, you partition all. In this case, parameters, gradients, or optimizer states, all of them. So, but stage 3 is a little bit different because if you partition a parameter, in that case, what we do is every time you reach a new layer, you need to gather all the parameters because the parameters are all sharded. Then what you do is all gather the parameters and then compute the layer. After you finish computing the layer, you can discard the data and then move to the next layer. That's what deep stage does. And then, actually, so many users complain that stage 3 is too slow. And stage 1, stage 2, so probably you don't see much difference in the performance. But stage 3, it is clearly slower than the other 2 stages. But anyway, you can see this as a kind of a trade-off between the performance and memory saving. This table shows the estimated model size. Originally, 20, but if you use your stage 1, that will be less than 5. It's stage 2, it will be less than 3. And 0 stage 3, it's really very small. And also another direction is offloading. Deep speed actually has a feature to offload both optimizer states or optimizer states plus parameters. Also, this adds a lot of overhead, but in some environment or for deep speed 0, if you have a sufficient number of GPUs in data parallel group, the memory saving will be good. But the number of GPUs are limited in that case. Also, the memory saving is limited. So offload is also useful in that case. You can offload the parameter or optimizer states to CPU memory. But if you want to do it very extremely, so we also have a way to offload the data to the high-speed storage, NVMe storage. So the paper published from DeepSpeed was a little bit outdated, but then when they first tried this Zero Infinity, which uses NVMe storage, if I remember correctly, using a DGX with 16 V100, they were able to train 1 trillion models, which is very big. So also let me mention this, the 3D progression. I think this team is also known to train MDTLG model with NVIDIA. The model had 530 billion parameters. And it was the world's largest model at the time of its release. It combines tensor parallelism, pipeline parallelism, and data parallelism, in this case also with zero. So now this idea is very common, known as 3D parallelism. Probably this was the first famous work used 3D parallelism to train the real scale models. So this is a basic feature. Deep speed. And then actually all of the users of DeepSeek use zero. Today I want to talk about more recent and advanced features. Let me begin with DeepSeek releases. So obviously there's a growing demand of training with long sequences. So sometimes Gemini says so they can handle 1 million token sequence or sometimes 10 million. That's great. DeepSpeed release is a technique, basically, technique to optimize long sequence training. It basically partitions activation along the sequence dimension, but ring attention or Megatron sequence parallelism. So all the other well-known long sequence algorithms do the same. The difference is Ulysses uses all-to-all communication for attention computations. So sometimes people say, so people are not very familiar with all-to-all communication. So just let me briefly explain how the all-to-all works, especially in our application. So I took this figure from this page when they optimize all-to-all, they publish a lot. And this is very useful. But anyway, I found this figure here. So you have a matrix, and then so assume your matrix partitioned on multiple GPUs. In this case, each column is on each GPU. Because GPU P0 has the data A0, B0, C0, D0, and the same goes for other GPUs. But when you apply all to this matrix on the left hand, you will get the one on the right hand. In this case, it is kind of transposed, and then the original column is now it's a row, and then the GPU P0 has it from A0, A1, A2, A3, and so if you apply all to the matrix on the right hand, actually the result will be like the left one in the left hand. So you are transposing. So we apply this communication to transformers in this, especially for attention what I would say. This figure is really complicated. Characters are too small. But this is showing the structure of transformer layer. So the left part is probably I believe you're super familiar with what computation is. Just I try to depict the structure. So the left hand, so you're computing QKD, and then the center part is attention. So the reason you see the kind of duplicated rectangles, so we have multiple heads. So each box tries to represent each head. And then after you compute the attention, you will kind of do a lot more or compute the output of attention. That's a normal attention. But what we do for DeepSeek releases is when you enter, before you enter the attention block, you will apply the all-to-all communication to activation. In that case, before the activation, before the attention block, the activation is partitioned along the sequence dimension. But using the all-to-all communication, you can change the dimension for the partitioning. After the all-to-all, you will have the activation partitioned in head dimension. Then you can naturally compute attention because so on each CPU, you have the entire sequence. The difficulty of partitioning or parallelizing long sequences. So to do attention, you need the entire sequence. That's the idea. But in this case, so you can have activations partitioned across sequence dimension other than attention block. That's the idea. So after you computed the attention block, next you can apply all-to-all again. That will actually change the dimensions for partitioning. So in the attention block, you have the activations partition in the dimension, but after the second auto, you can get that activation back to the original partitioning state. That's what we did in ECE. The idea is very simple, but one of the key advantages of this idea is in some environment, like for example, or in DGX type network or kind of fat tree type network, this where each GPU has the dedicated link. In that case, so all the data communicated across GPUs has exactly the same size. Then, so if you have the dedicated link for each GPU pair, you will never have the contention of the communication. Then this works very fast. So given the message size is M and you have P GPUs in this case, the communication overhead will be OM over P. So that means when you increase the sequence length, and if you can increase the number of GPUs proportionally, in that case, you can keep the communication overhead of this auto consistent. Then, so if you compare with other approaches like sequence parallelism implemented in Megatron LM, actually it uses all gather, but all gather's overhead is OM in this case. So if you, even though you increase the number of GPUs, if you increase the sequence length, the overhead of the communication. But ECE, you can keep it constant. That's the clear advantage of our method. So using this, even with a little bit limited GPU environment, we use a 140 gig. That explained was algorithms cluster. And then when the model is small, you could train 1 million contexts. Also, in terms of the efficiency, it showed significantly better throughput for large models. It was for 1660 models. It was much faster than Megatron's approach. And then also the maximum length of the sequence is also significantly larger. That was the result. But probably I wonder if all of you might have a question about what is a comparison with ring attention. Because ring attention is now the most popular approach for training long sequence, I guess. So, but I don't have the thorough experiment results because actually we published this paper last summer. And then the ring attention paper from UCB was published after that. Then I didn't have a chance to compare the two, but actually, so our research group from Tencent proposed a very interesting approach to combine the deep sea ECE ring attention. Or in the paper, they also did a very thorough analysis of the two approaches. I just found that this table in their paper, this is not a result. But in the column of this paper, ECE's degree, that shows a kind of combination of the two approaches. That means if you have 8 GPUs in, for example, if the ECE's degree is 8, that means you use all GPUs for deep ECEs. And the number is 1, that means that will be pure ring attention. So if you look at the kind of basic ring, you see that the ECE is much further than ring attention. So, and they also compared with the different sequence lengths, 32K and 128K. But so for that basic ring part, ECE is significantly faster. But so they also did some improvement on load balancing across GPUs. And then in that case, for the shorter sequence in this table, ECE is still better. Longer run, the ring attention is a little bit better, unfortunately for us. Anyway, I think this is the latest results about the comparison of our approaches. Actually, I met some users of ECEs, sometimes startups, sometimes research institute. They said ECE is first, but they also wanted to integrate this approach. I just wanted to work with people algorithm to integrate this approach to Megatron, the Megatron deep scheme. Yeah, and also regarding long sequence training, this is a very recent work. This was done with the intern in our team last summer from Ohio State University. So for this one, so usually, okay, if we remember what the assumption is, I said when the sequence length increase, if you can increase the number of GPUs proportionally, yeah, you can train it. But of course, GPUs are always very expensive, and then so resources are limited. So this work tried to address this issue. So what we did was activation. Activation is also grows proportionally to the sequence length. And then if you look at the memory usage is in the transformer, this table shows that memory usage, but you find that in, for example, in attention block, in the forward pass, depending on your activation size, it will require a lot of memory. For forward, it will require 4 MB, because N is number of heads, and D is the hidden size. Then sorry, this is so notation should be different. N should be in this case a sequence length, and D should be the total hidden dimension. But anyway, for forward you will need 4 MB. Then backward that will be 8 MB, and that same goes for FFM. This memory usage is actually significant when you run with a very long sequence. So it is even more than the parameters of optimizer states. Also, if you use 0 and you have some GPs, you can reduce the memory for parameters of optimizers. But for activation, 0 does not address the memory size of the memory usage for activation. We need to do something. Then, so what we did was GPU chunking and sequence offloading, double buffering. This shows the methodology. Basically, what we did was to compute attention in pipeline fashion. So it's like online attention in flash attention. So this figure tried to depict how it works. So basically, once you use UACs, you partition the sequence. But we partition the sequence further. In this case, you can have multiple chunks. And then in this figure, from the second chunk, you took QKB from the second chunk. And then first, you can do part of the attention computation by using Q2 and K2 and K2. But in the next step, you could choose different pair of KD. And then you can compute the other part using that Q2 and the next pair of KD. You can do it in a kind of pipeline fashion. So one trick to save the memory is after you finish using the KV pair, you offload it. But in this case, our target is a really long sequence. So the computational cost of attention will be ON square if the sequence is N. But the offloading overhead is, of course, ON. In that case, you have a sufficient length of sequence. In that case, you can completely hide the overhead of offloading. That's the idea. Then actually this showed a very good result. Just using 4A100 with 80 GB memory, then the model was 6.7 billion. We were able to train 2 million token sequence, which was actually 16 longer sequence than the soda. Also, we observed a very good teraflops because yes, you are offloading. This is overhead. But if you have a really long sequence, so the computational efficiency of the attention part will be very good. So that was the result. That is about the sequence. Sorry. Then that is about long sequence training.
Question on this before we switch to the next one.
Yep.
Like how many inputs can you find with 2 million context and is scaling in the context length dimension the key challenge now, or need to do that alongside scaling parameters?
So Can you say those questions?
So maybe the first part is, do you have enough training data that is too
That's a good question. Okay, in this case, I would say we just focus on the computational efficiency, the feasibility, how we can fit the model and the sequence into GPUs. But I think the possible challenges of maybe the one of our promising application is kind of multimodal or images. So actually, some users reach out to us about long sequence was one was about medical record processing. So in their cases, so they wanted to combine all the medical records, including both text and images. That's one. Another one was about the video processing. So the user didn't show much about that, probably, but that is about video generation, I guess. Well, so I didn't see, but so another possible application is probably you have a large code base, and then you want to give a question about the code or coding assistant can be the good application. What was your next question?
I guess the second part is more broadly, like, is the key challenge now to scale context length even more, or is it to train larger models? Like some people are saying, okay, in terms of number of parameters, things are plateauing. Is now the challenge just the context length, or do we still need to think about both just from your perspective?
A really good question. I don't have a clear answer to that, but my impression is even for the largest companies in this field, of course, we have the limitation about model scales. Then, so extending a sequence length is a little more, I don't know, promising just by increasing model sizes because of, for attention, but you could do a little bit more about sparse attention, some kind of algorithm tricks, but just increasing the parameters. Yeah, maybe, but I don't have a clear answer.
Right, okay, fair enough.
I also have a question. So when you try to chunk or prefer like all to all, is this compatible with like a flash attention to avoid like?
Yes, very good question. Yes, actually this is compatible because if you look at this figure, the blue part is attention, but the input and the output of the blue part is exactly the same as the traditional.
So basically, I can considering like we parallel along the head dimensions.
Yes.
But in this cases, let's say head dimension is only up to like 128. Does it mean that we can only scale it up to like 128 GPU?
Exactly. This is a very good question. So this method is related to the number of heads. So this is actually sometimes an issue because you said so if the head is 128, yes, but 128 is good, large enough in many cases. But sometimes it's fewer, especially if you use GQA or something.
Yeah.
The KNB can be much smaller. In that case, yes, this is limited.
I see.
This is a very, very good question. Okay. This is about MOE. So yeah, so MOE is now very popular. Suddenly, so many people started adopting MOE in the models. Maybe probably it started from next year, but we also trained 5.3 MOE. I worked on that. So some other latest models uses it. DeepSphere MOE was released in January 2022. It was a little bit earlier than the recent trend of MOE. So I would say also. So I think DeepSphere MOE is one of the initial efforts to implement expert parallelism for very large scale MOE model. So it showed very high efficient implementation of expert parallelism. In the first paper, we showed that by using that implementation, we can achieve the same model quality. It's much smaller computation budget. That was one result. And then, so another one is we also proposed a new architecture, MI architecture which we call pyramid residual MOE. Here we have different number of experts, different layers. So by using this architecture, we also show that we can achieve the same quality with a significantly smaller model. So the last idea proposed in the paper was mixture of students. That was a distillation for MOE model. We observed a little bit worse model quality, but also we successfully reduced the computation cost. And then, so some of the results are a little bit outdated things. So let me move to the other part. This is about MOE first. In this paper, we also show some optimizations. The one is hierarchical, or the other one is computation with TensorFlow. The last one is optimized kernels. So first, let me show the results. Using these optimizations, they actually show the significant speed up over the naive PyTorch implementation. So I have 4 figures here, but if you look at the 1 trillion one, the model used here was 24 billion, 128 experts. This is so many considering the recent popular model. But anyway, but with this model, we observed more than 7 times speed up for inference. And also in this case, for 1 trillion model, the time for forward pass was just 25 milliseconds, which is quite close. So they use A100. Then the idea of hierarchical O2O was, in this case, the O2O was a little bit different from the O2O I mentioned for Ulysses. In this case, so you are using O2O for kind of distributed tokens to experts. In this case, the communication volume from the source to destination can be different from each communication path. So sometimes you have competition. The part is quite different. So basically, the O2O used here is much slower than the clean, perfectly balanced O2O. But anyway, so but in such a case, the communication overhead O2O is basically the number of hops of the communication. So you just each hop you send a piece of the data. But with this hierarchical O2O, you can reduce the number of hops. In this case, first you exchange the data within a node. Then in that case, you have GGPs. So that's a too small, very sorry for that. But if you have GGPs on the single node, in that case, to do the internal O2O, number of hops will be G. But then, so next step is internal O2O. But in this case, you have PGPs in total, but number of nodes will be P over G. Then number of hops will be P over G for the second O2O. The total communication overhead, in this case, is related to hops of the O2O will be OG plus P over G. So compared to the naive O2O, that will be OP, it can be significantly smaller. This is, of course, that depends on the number of GPUs and number of nodes. But with this approach, we drastically reduce the communication overhead. This is one of the ideas in DeepSpeed. The next one is combination with TP, tensor parallelism. Yeah, in tensor parallelism, you actually have the exactly same activation across different tensor parallelism ranks. That is a TP. So then, but in that case, as you have the duplicated data of different GPUs, you can just reduce the data communication, because if the data is already there, you don't need to send the data. So that's the idea. So basically, using TP contributes to reduce the latency, because in MOE, the balance between the loading of data and the computation is different. And so especially for MOE, the data loading part from HBM is a significant overhead. But using TP, you can reduce the data volume loaded from HBM per GPU. So first, we combine the expert parallel with TP, and also using the nature of TP, that where we have the duplicated data on GPU, we can reduce the communication volume. That was the another idea in DeepSpeed MOE. Okay, and then so actually I use deep speed MOE in a very serious case. Like first we first try to train the Phi3 MOE model. I did a lot of benchmarking for that. It actually showed a very good performance. In some cases, it was even faster than the not sparse approach. But it also depends on the case. Like, if you want to try, I'm very happy, but I also recommend that you need to benchmark before you start a serious large-scale training. Okay, deep speed TDD is the next work of the MOE optimization from deep speed team. I said they combine with tensor parallelism, but it was in the first paper, it was basically for inference. So they also combine all the different strategies, parallelization strategies for MOE, so training. And then they show that depending on the environment or the kind of model size of the condition, you by carefully choosing the combination of these different parallelisms, you can actually increase the throughput. We use this combination for the training of an internal model, which is a very large scale, more than 2,000 GPUs. And in that scale, actually, it's very important to have a different parallelization strategies because each different approach has a different limitations. So the combinations. We can talk about this later. So then, so lastly, let me mention something about compiler integration. This is a really ongoing work. Nothing is published. I'm actively working on it. I mean, I have a very strong attachment to this, but let me explain a little bit. So recently, PyTorch introduced a compiler in it. So the compiler uses some optimization like kernel fusion, or sometimes they use pattern matching or replacing operators more efficient ones. Like normally, if you find some patterns for attention, it will replace with more efficient one like SDPF or something. But usually it has a limitation, not only about PyTorch compiler. Basically, the deep learning compiler focus on optimization of a single GPU. That's one limitation. Another one is graph breaks. So PyTorch people did a really good job, but DL compilers basically work on the static computational graphs. That means, so if you have conditional behaviors, actually PyTorch is very, very flexible. You can do anything in the model implementation, but this probably the design of the PyTorch compilers suffering from that flexibility. So if you have some conditional behaviors like conditional branches or loops in the model implementation, the only way they could do is just they will break the graph into smaller pieces. And then, so for the conditional part, they let Python interpret the hardware. Then that is the limitation. Actually, if you have a lot of graph breaks in your model, actually the performance will be bad. You can actually observe that. So, but in some cases, like for example, we have DeepSpeed 03. So for that, we have so many complicated processes for 03. Like for example, if you add complicated hooks to the model and then trace the execution orders and then launch prefetching or something like that. But PyTorch compiler cannot capture this kind of complicated behaviors. And then finally, it leads to a lot of graph break performance feedback. So that's one of the limitations. So what we did, what we are trying to do is optimization, more compiler for more native compiler for distributed workload. What I'm working on is optimization include, how should I say, this kind of include some optimization for distributed workload in the scope of the compiler. For example, communication scheduling or more detailed memory analysis or something like that. The workflow is So I show the workflow on the right hand. First, basically you start with training script, but you have a model implementation. Then, so basically PyTorch compiler compiles the model and it extracts a computation graph. And sometimes it does some optimization like fusion. But we have another layer for deep speech compiler. Then what we do here is to add some communication operators or scheduling as communication or optimization based on your prioritization strategy. That part is not covered by the traditional VM compilers. We're working on that. For example, this is a very simple example to achieve 0.3 with the compiler. Now, PyTorch can extract the graph like the one on the left hand. So that you have the trainable parameter. It is used by two operators 1. But so what we do is just to add all together, because so if you do some kind of partitioning strategy like 0.3 or FSTP, the parameter is actually sharded. You need to all gather the parameter before you use it. Then in this case, it automatically analyzes, the compiler analyzes the dependency of the operators and data, and then insert all gather operator. And in this example, you can also find that the last user of the parameter is operator 3. So, and then only after you finish computing operator 3, you can release the buffer of the all-gather result. So by doing some kind of lifetime analysis, you can find what is the shortest lifetime of this data or something like that. So then, so by doing this approach, you can avoid the overhead by graphics. So this is actually already working on real example. So applying to gamma 3, yeah, it is a little bit more complicated because this is a real model. But this is a parameter, embedding parameter, and it is used for embedding operator. But in this case, if you're using it, you can all gather. But in reality, it's a little bit more complicated. You need to make sure the communication finishes before you use it. But anyway, after you use it. And then, but if you do this level of very fine-grained analysis, and then in this case, you are handling each operator in computational graph. Then if you trace the graph, you have the complete information, like how much memory you need at each point. So by using this kind of very detailed information, you can try so many funny things. One is a more aggressive prefetching. So now DeepSpeed and FSTP all have prefetching, some kind of prefetching, but usually you can just preset the specific size buffer. Then so until your buffer is full, you can prefetch it. That's what we do right now. But in this case, you have more detailed information at each point. Then in that case, soon after you start forward pass or backward pass, you know how much memory is available. Then you can launch as many algorithms as possible earlier. Then you will get more chances to make them overlap. So actually using this approach, I observed a very good improvement. Like this one is pretty big, I think. For example, for mixture with 2K sequence, and then in this case, 40% speed up. Just by in this case, user doesn't need to change anything. All are handled by compiler. So you can apply this optimization to all kinds of, for example, Hugging Face model without any manual user effort. Also, unfortunately, I recently found out that the Meta did a very similar optimization. So the archive paper was published 2 weeks ago. I was kind of shocked. Anyway, so our goal is to provide a platform to enable user to play with this kind of various optimizations. So we will offer APIs to register your custom optimization paths. Also, what you need is actually, so adding some node to computational graph is not so difficult. The hardest part is how you kind of evaluate it, the memory usage. So that part is the role of infrastructure for this system. But by using this system, your custom optimization path can have an access to that profilers or any information. So the next step is, so based on the memory profiling, you can do something like adaptive offloading or more like selective activation checkpointing or something like that. Or using pattern matching and some communication features, you can automate some kind of parallelism, like sequence parallelism or tensor parallelism. Especially for sequence parallelism, it does not relate to the parameters. I mean, the parameters placement is the same with sequence parallelism. You can just change the operators. Or another interesting topic could be model-specific optimization, because you can easily add your own custom optimization paths. So you can, I don't know, write a kind of tailored optimization for your model. Like, for example, one interesting example is communication scheduling for MOE. Anyway, that's ongoing. It's already 50 minutes. Okay, let me just quickly go over the results. So I have introduced some of the key features of DXP. What I want to share is a little bit more random thought about this field. So I have been involved in multiple large-scale training projects. Sometimes the models are more than 100 billion. Sometimes the GPUs are more than 2,000. But I have seen some common issues and then some common topics. I just wanted to share some of the random ideas just to discuss the next steps for, I don't know, discussion. The first one is, as I mentioned, this is something about the different strategy for parallelization, the combination. For that, for example, once you join the large-scale training project, so actually the first thing you need to discuss is how you should combine different parallelization strategies. So there are so many factors you need to think. If you have hundreds or thousands of GPUs, of course you need DP, but also you need to think about the global batch size limitation. And so DP might be good, of course, but internal communication must be first or something like that. So then usually, I don't know. So first, you normally start from a simple approach, and then so you gradually, I don't know, once you get some confidence in your model or design or setting, you can invest more in efficiency optimization. Okay, so the time is limited. Let's move on to the next one. So also the recent common discussion I have seen is balance between robustness and efficiency. One good example I saw was FP8. FP8 actually improves teraflops very well, but it's also potentially diminishes the model quality downstream tasks. The hard part is that the impact will be revealed only after you trained a lot. So after you trained, for example, 2 weeks, 3 weeks, using hundreds of GPU, then you will find that quality of the downstream task is bad. This is really, really bad. So then I haven't seen a lot of published work until very recently, but so yeah, but this, yeah, recently I found some papers, some I mentioned 2 papers here. The one conclusion I saw in the first paper was if you do some quantization or string or pre-training. So as you train the model with many tokens, the negative effect will be even bigger or something like that. Now we have this kind of insights. First, you definitely need to refer to this paper, but always a real workload is complicated. What you can do is just to constantly evaluate the downstream tasks. All the project I saw follow the same path. First, they will try something new and then observe the bad result, and they finally reach the same conclusion. Oh, we need to have a very well-designed evaluation pipeline. I threw this 3 times, but if you have a chance to join this project, yeah, you should definitely set up a good evaluation pipeline. Anyway, so the next topic is resilience and elasticity. The availability of GPUs are always changes. Sometimes people say, oh, Microsoft is a big company, you should have a sufficient number of GPUs. But it's not always true. Always the priority of GPU changes. Also, we have other issues. And then so even when we have a sufficient amount of GPUs, so depending on the tasks and the hardware scale available is different. You may be able to use thousands of GPUs, but for fine tuning, the priority is different. What you want to do is to sweep different conditions in that case. Instead of running a super large single job, you need to probably run many smaller jobs in that case. But if the hardware scale is different, best prioritization strategies can also be different. In that case, flexibility regarding the prioritization strategy is very important. So even when you start the project, you need to be aware of that. So, oh, we have this very good training pipeline, it is already available, you can use it. You may think that way, but so later you may need to run the same model in a different environment. That's one thing I wanted to share. And also that this is also similar topic. So when always model science are excited, like, so by changing a model like this or just extending this layer, then we can get a little bit better results. So you need to be very aware of how you can run the model in production. If you have an idea to run it in production, like so, yeah. So 5.3 MOE has 42 billion parameters, but if you run it in BF16, it will be 84 gigabytes. This is really bad because most of the GPUs sometimes 80 gigabytes. If your model is 84, this is really bad. So quantization works. This is good. Actually, it's very easy to reduce memory footprint for model parameters. But implementing the kernel for quantization is sometimes tricky. So because in inference serving, you also need to consider a wide range of batch sizes. But depending on the batch size, your optimization strategy in the kernel can be different. This makes the implementation hard. The last topic is the complicated pipeline. So sometimes, for example, RLHF for similar pipelines very popular recently. For example, in RLHF, you have multiple models after critical reorder inference and sometimes. And so they are actually complicated. Some models are updated, but some models weights are frozen. So also another complexity is they have multiple phases. First, they generate the experience, but this is only inference. Then after that, using the generated experience, we will update after the critic. This is training. Well, how we can deploy it? So if you can allocate the dedicated GPUs to each models, so but you are not using all the GPUs at the same time, which is a serious inefficiency. Multiple groups have tried to address this issue. We also did that. One was deep speed chat. We tried to let multiple models to share the same GPU set using offloading or some system optimization. So another popular framework is OpenRLHF. It's basically extended deep speed chat, but you also combine deep speed and relevant for efficient generation. That's how you by carefully analyzing the workload. Yeah, I think about this part is very interesting. There's still a lot of opportunity for exploration because so in a traditional training pipeline, you just run forward back one parameter. This is very simple, probably just not so much depth for further optimization. But if your pipeline is more complicated, you have more chances to do something. But anyway, yeah, this is, I already mentioned something, but your acceleration. Yeah, and that's basically that's it. We are open source software. We have a very large community. We mentioned some cross collaborators, but we are always happy to collaborate. That's it. Thank you very much.